Hi everyone. Today I'm going to talk about static code analysis for Lustre. As every distributed file system, Lustre is a quite complicated piece of software. However, people rely on it for their data, so it has to be reliable. One of the things we can do to increase its reliability is to remove the bugs it contains. And one of the ways to do so could be to use such a tool. So the objective of my presentation is to show how the whole Lustre community can benefit from the work we are doing at Bull with Coverity. Here's the agenda of my presentation. So after a general presentation of Coverity, I will show how we use it at Bull, the results we got so far, and how everybody can get benefit from it. But first of all, we can wonder why doing static code analysis. A first answer to that question can be found on the HPDD Wiki's page entitled Project Ideas, where it is stated that a static code analysis tool can help identify potential latent bugs in the Lustre code. Those bugs are hard to find through testing, but are easy to fix once found. I also like this quote from Humphrey, stating that even good developers would add a mistake for every 7 to 10 lines of code they write. So now, knowing that Lustre is more than 540,000 lines of code, you had a good potential here. Now, a general presentation of the tool. Basically, this tool has to compile code in order to analyze it. So we build with a specific command that uses a Coverity tool. Then the build sources can be analyzed. This is the second phase of the Coverity workflow. At this stage, we have a variety of checkers. Each one is dedicated to a specific task, like checking for uninitialized variables, resource leaks, and so on. Once the analysis is complete, all results are stored in a database, and this database can be accessed with a web interface. Here's a screenshot showing the overall aspect of this web interface. No matter if you can read, if you can't read the lines, it's just to give an overview of it. On the left side, you can filter the defects. In the middle, you have the list of defects that you choose to browse. Just below, you have a code browser. This code browser is enhanced with annotations and explanations on the bug that is currently being inspected. And on the right side, you can comment on the bug, assign a developer and a severity. Now, to end with this general presentation of Coverity, is the list of defect categories Coverity can find. As you can see, there are a lot of potential sources of errors. Coverity can check from very basic things like resource leaks to much more complex ones like program hangs. Now, how do we use Coverity at Bull? After discussing with some developers at Intel, we decided to run this tool on the master branch. That way, it would be much more easier to propose patches to fix the issues found by the tool. However, we still run Coverity on the 2.1 branch, just in case we found really major issues. On the master branch, the last tag we analyzed is 2363. The 2364 was just created a few days ago, and we plan to run Coverity on every new tag until 2.4 GA. Now the results we got. When running Coverity on 2363, we found 301 defects. Among those defects, on the right side of the diagram, you have the bugs. So we have 195 bugs found by Coverity on the Lustre code. So we have filtered those defects depending on their severity from major to moderate and minor. On the left side of the diagram, you have what I call the not real bugs. So these are false positives and intentionals. False positives are cases where Coverity made a wrong analysis of the situation. So in fact, there is no problem at all. And intentionals are a correct evaluation of the situation made by the tool, but in fact it corresponds to an intentional, to something intentional from the developer. The problem with those false positive and intentional bugs is that they represent a waste of time. We have to analyze them in order to finally realize that they are not real bugs. So we would like to avoid them as much as possible. It's quite easy for some kinds of intentional bugs like fall through in switch cases, and simply a comment by the developer saying falling through can be understood by the Coverity tool, and then it does not raise any defect. Avoiding false positive can be much more tricky. For example, we have a bunch of false positives with, due to function pointers, they represent a very complex code path, and simply Coverity get lost. So we could imagine redesigning the code in order to make it simpler and gain maintainability on that. But in a shorter term, we could use Coverity-specific comments that would avoid the tool to raise errors and defects. Now, if we look at the 195 bugs, 195 bugs found by Coverity, this diagram shows the categories these bugs belong to. As you can see, we have a majority of null pointer dereferences. We also have control flow issues, and the third category is security best practice violations, like buffer copies without checking boundaries. Now, if we look at what we got when we analyzed the Lustre code on every tag that was created on the master branch. The blue bar represents the bugs found by Coverity on each tag. You also have on top of the blue bar a purple bar representing the defects that were fixed on each tag. So if we pile up those two bars, we obtain the number of bugs that Coverity would have found if we had not submitted patches to fix the defects. The red line represents the code modifications made between two consecutive tags. This is why we start at 0 with 2350, which was our first reference tag. And what this diagram shows is that the defects found, the bugs found by Coverity increase with the number of lines changed in the Lustre code at each tag. Every time we have a large amount of code that is modified, developers create new bugs that are found by Coverity. The other thing shown by this diagram is that the blue bar only decrease because we submitted patches to address issues found by Coverity. I mean, those bugs don't just vanish by themselves when code evolves. If we do the same exercise on the maintenance branch, we can see that this is the same. I mean, the number of bugs found by Coverity also increases between 2.1.0 and 2.1.5. Now, if we have a look specifically at which bugs were created and which bugs were removed, we notice that only 3 bugs, Coverity bugs, were removed from 2.1.0 to 2.1.5. The first 2 ones were removed by Jira tickets that are completely unrelated to the bug found by Coverity. So this is just that the code was redesigned and the error found by Coverity was removed at the same time. The third one, a logically dead code issue, was fixed by LU 570, and we could consider that this Jira ticket is related to the logically dead code issue in Lustre PO.C. But this Jira ticket is not a customer defect. So in the same time, 11 new Coverity bugs were introduced between 2.1.0 and 2.1.5. So we have a +8 on the number of bugs found by Coverity. What does that mean? Well, in fact, we found out that fixing customer bugs is completely unrelated to improving code quality. We can do both at the same time. They are compatible, and improving code quality by itself is useful with Coverity. Now, how can we make the whole Lustre community benefit from our work? We would like to share the defect list generated by Coverity. Unfortunately, this is not really easy. The best we can do is export the list in a CSV or XML format. And as you can see, it's completely useless, because at best you get a function name and a type of a category of error. So this is not so easy to then fix the issue. And for licensing reasons, we cannot give access to the web interface. This is why we decided to open Jira tickets to address the bugs found by Coverity. So far, we have opened 30 Jira tickets that cover all bugs found by Coverity. They're identified with the Coverity label if you do a search on the Jira interface. 13 have been merged so far, and I'd like to thank Intel's responsiveness on that aspect. Of course, we hope that as many patches as possible will be landed before 2.4 GA. And even after 2.4 GA, our goal is to continue to use Coverity on the Lustre code. So as a conclusion, this presentation summarizes a 6 months work. As we found out, improving code quality is different from fixing customer bugs. This is why we are convinced it is still useful to use Coverity, because in the end it will help improve the overall quality of the code and of course the stability of the Lustre products. Thank you.
have 4 more minutes. We can field some questions if you have any.
So Coverity provides pretty liberal access to open source projects. And one of my play toys, they do the analysis and put it up for free. So have you talked with them about enabling the web access to the results for Lustre?
As far as I know, they make available, for example, what they get when they run their project on the kernel code, for instance. But to me, you can only see a defect list, but then you cannot have access to the detail of each defect. Am I right? It seems that this is just an advertisement for their product, but in the end, you cannot really use what they show to really fix defects.
Well, for my toy and for NTP, I was able to get detailed access to what the issues were.
Okay.
But obviously, I couldn't initiate a new run on the data.
Okay.
But I could see the results, all the results.
So a question of benchmark, because I'm a benchmark guy. So did you try maybe to look in the areas where there are bugs found and fixed in Jira, and maybe to see if do you have enough details or could have fixed them if you would run the Coverity? Or?
I'm sorry, I didn't catch your point.
So let's suppose that there are some fixes in Jira that already. So you could have gone in the previous release and run Coverity to see if they will find, because you said customers' bugs are not detectable, but maybe they are, but we don't know how to interpret. I have bad experience with Coverity. They are good in detecting, but it's very difficult to figure out exactly. So did you try that? I think maybe it's a good idea to,
Basically, this is what we tried when analyzing what was done on the 2.1 branch.
So were you able to detect the same bugs and address them?
Unfortunately, no. So, I mean, this is what I tried to explain. Bugs found by customers, and that could lead to crash, for example, are not bugs that could be found by Coverity.
No, I understand that maybe as a benchmark to see are there any?
Yeah, I don't know.
We're out of time. Thank you, Sebastien.
Thank you.